Hello and welcome to the session on transformation of mapping. We know that the real function y equal to f of x can be represented graphically by a curve in the xy plane. Also, the real function z equal to f of xy can be represented by a surface in three-dimensional space. However, this method of graphical representation fails in the case of complex functions because a complex function w equal to f of z, that is u plus iv is equal to f of x plus iy, involves four real variables, two independent variables x comma y and two dependent variables u comma v. Thus, a four-dimensional region is required to represent it graphically in the Cartesian fashion. As it is not possible, we choose two complex planes and call them z plane and w plane. In the z plane, we plot the point z equal to x plus iy, and in the w plane, we plot the corresponding point w is equal to u plus iv. Thus, the function w is equal to f of z defines a correspondence between the points of these two planes. If the point z describes some curve c in the z plane, the point w will move along a corresponding curve c dash in the w plane. Since to each ordered pair xy there corresponds a point ordered pair uv, the function w equal to f of z thus defines a mapping or transformation of the z plane into the w plane. The image of a point z in the domain of definition S is the point w equal to f of z, and the set of images of all points in a set T that is contained in S is called the image of T. The image of the entire domain of definition S is called the range of f. The inverse image of a point w is a set of all points z in the domain of definition of f that have w as their image. The inverse image of a point may contain just one point, many points or none at all. Terms such as translation, rotation and reflection are used to convey dominant geometric characteristics of certain mappings. Translation: w is equal to z plus c, where c is a complex constant. Let z is equal to x plus iy, c is equal to a plus ib and w is equal to u plus iv. Then the transformation becomes u plus iv is equal to x plus iy plus a plus ib. That is, u plus iv is equal to x plus a plus I times y plus b. That means u is equal to x plus a and v is equal to y plus b. Thus, the transformation is a mere translation of the axis and preserves the shape and size. Examples: consider the transformation w is equal to z plus 1 minus I. Let us determine the region d dash of the w plane corresponding to the rectangular region d in the z plane, bounded by x equal to 0, y equal to 0, x equal to 1 and y equal to 2. Given w is equal to z plus 1 minus I, that is x plus iy plus 1 minus I, which is equal to x plus 1 plus I times y minus 1. W is equal to u plus iv implies u is x plus 1 and v is equal to y minus 1. Let us draw the rectangle D in the z plane. Hence, the lines x equal to 0, y equal to 0, x equal to 1 and y equal to 2 in the z plane are mapped onto the lines u equal to 1, v equal to minus 1, u equal to 2 and v equal to 1 in the w plane. Thus, d dash in the w plane is like this. Now coming to rotation and magnification. W is equal to Cz, where C is a complex constant. Let C is equal to rho e raised to I alpha. Z is equal to r e raised to I theta and w is equal to capital R e raised to I phi. Then the transformation becomes r e raised to I phi is equal to rho r e raised to I times alpha plus theta. So that capital R is equal to rho r and phi is equal to theta plus alpha. Thus, the transformation maps a point P ordered pair r theta in the z plane into a point P dash ordered pair rho r comma theta plus alpha in the w plane. Hence, the transformation consists of magnification of the radius vector of rho by rho is equal to modulus of c and its rotation through an angle theta. It maps figures in the z plane into geometrically similar figures in the w plane. Now consider the example 2. Consider the transformation w is equal to z e raised to I pi by 4 and determine the region in the w plane corresponding to the triangular region bounded by the lines x equal to 0, y equal to 0 and x plus y equal to 1 in the z plane. The given transformation is w is equal to u plus iv, which is equal to cos pi by 4 plus I sin pi by 4 into x plus iy, which is equal to 1 by root 2 times 1 plus I into x plus iy, which is equal to 1 by root 2 times x minus y plus I times x plus y. Thus, u is equal to 1 by root 2 times x minus y and v is equal to 1 by root 2 times x plus y. The line x equal to 0 maps into u is equal to minus 1 by root 2 y and v is equal to 1 by root 2 y or v is equal to minus u. The line y equal to 0 maps into u is equal to 1 by root 2 x or u is equal to v. The line x plus y equal to 1 maps into v is equal to 1 by root 2. Now consider inversion. W is equal to 1 by z. Let x is equal to small r e raised to I theta and w is equal to capital R e raised to I phi. Then the transformation becomes capital R e raised to I phi is equal to 1 by small r e raised to minus I theta. So that capital R is equal to 1 by small r and phi is equal to minus theta. Thus, under the transformation w is equal to 1 by z, a point P r theta in the z plane is mapped into the point P dash 1 by r minus theta. The transformation w equal to 1 by z maps the interior of the unit circle mod z equal to 1 into the exterior of the unit circle mod w is equal to 1 and the exterior of mod z equal to 1 into the interior of mod w is equal to 1. However, the origin z equal to 0 is mapped to the point w is equal to infinity called the point at infinity. Now consider an example. The transformation w is equal to 1 by z maps a circle in z plane to a circle in the w plane or to a straight line if the circle in the z plane passes through the origin. The general equation of any circle in the z plane is x square plus y square plus 2gx plus 2fy plus c is equal to 0. That is equation number 1. Let w is equal to u plus iv, that is equal to 1 by z. Then z is equal to 1 by w, that is x plus iy is equal to 1 by u plus iv, which is equal to u minus iv divided by u square plus v square. So that x is equal to u by u square plus v square and y is equal to minus v by u square plus v square, that is equation number 2. Put 2 in equation 1, that is u square divided by u square plus v square whole square plus v square divided by u square plus v square whole square plus 2gu divided by u square plus v square minus 2fv divided by u square plus v square plus c is equal to 0, which implies u square plus v square divided by u square plus v square whole square plus 2gu divided by u square plus v square minus 2fv divided by u square plus v square plus c is equal to 0, which implies 1 by u square plus v square plus 2gu divided by u square plus v square minus 2fv divided by u square plus v square plus c is equal to 0, which implies c into u square plus v square plus 2gu minus 2fv plus 1 is equal to 0, which is the equation number 3. If c not equal to 0, the circle 1 does not pass through the origin and 3 represents a circle in the w plane. If c is equal to 0, 1 passes through the origin and 3 reduces to 2gu minus 2fv plus 1 is equal to 0, which is a straight line in the w plane. Note that regarding a straight line as a circle of infinite radius, we can say that the transformation w is equal to 1 by z maps circles into circles. Consider another example. Under the transformation w equal to 1 by z, find the image of modulus of z minus 2i is equal to 2. Given that w is equal to 1 by z, which implies z is equal to 1 by w, that is x plus iy is equal to 1 by u plus iv, which is equal to u minus iv divided by u square plus v square, which implies x is equal to u by u square plus v square and y is equal to minus v by u square plus v square. The given circle is modulus of z minus 2i is equal to 2 or modulus of x plus I times y minus 2 is equal to 2, that is x square plus y minus 2 whole square is equal to 4, which implies x square plus y square minus 4y is equal to 0, which is a circle in the z plane with center ordered pair 0, 2 and radius 2. That is x square plus y square minus 4y equal to 0 implies u square by u square plus v square plus v square by u square plus v square whole square plus 4v divided by u square plus v square is equal to 0, which implies 1 plus 4v equal to 0, which is a straight line, which is the required image of the given curve. Now consider an example. Find the image of the infinite strip 1 by 4 less than or equal to y less than or equal to 1 by 2 under the transformation w is equal to 1 by z. Also show the regions graphically. We have w is equal to 1 by z, that implies z is equal to 1 by w, that is x plus iy is equal to 1 by u plus iv, which is equal to u minus iv divided by u square plus v square, that is x is equal to u divided by u square plus v square and y is equal to minus v divided by u square plus v square. If y is equal to 1 by 4, then minus v divided by u square plus v square is equal to 1 by 4, which implies u square plus v square plus 4v is equal to 0, that is u square plus v plus 2 whole square is equal to 4. If y is equal to half, then minus v divided by u square plus v square equal to half, which implies u square plus v square plus 2v is equal to 0, that is u square plus v plus 1 whole square equal to 1. Hence, the infinite strip 1 by 4 less than or equal to y less than or equal to 1 by 2 mapped into the region between the two circles u square plus v plus 2 whole square equal to 4 and u square plus v plus 1 whole square equal to 1. Bilinear transformations or fractional linear transformations. In geometry and complex analysis, a Mobius transformation of the plane is a rational function of the form f of z is equal to az plus b divided by cz plus d of one complex variable z. Here the coefficients a, b, c, d are complex numbers satisfying ad minus bz not equal to 0. Geometrically, a Mobius transformation can be obtained by first performing stereographic projection from the plane to the unit 2 sphere, rotating and moving the sphere to a new location and orientation in space, and then performing stereographic projection from the new position of the sphere to the plane. These transformations preserve angles, map every straight line to a line or circle, and map every circle to a line or circle. The set of all Mobius transformations forms a group called the Mobius group, which together with its subgroups finds numerous applications in mathematics and physics. Mobius transformations are named in honor of August Ferdinand Mobius. They are also variously named homographic transformations, linear fractional transformations, bilinear transformations, or fractional linear transformations. Decomposition and elementary properties. A Mobius transformation is equivalent to a sequence of simpler transformations, let translation by d by c, inversion and reflection with respect to real axis, dilation and rotation, translation by a by c. Then these functions can be composed giving f of z equal to az plus b divided by cz plus d. This decomposition makes many properties of the Mobius transformation obvious. The existence of the inverse Mobius transformation and its explicit formula are easily derived by the decomposition of the inverse functions of the simpler transformations, that is, define functions g1, g2, g3, g4 such that each gi is the inverse of fi. Then the composition gives a formula for the inverse. Preservation of angles and generalized circles. From this decomposition, we see that Mobius transformation carry over all non-trivial properties of circle inversion. For example, the preservation of angles is reduced to proving that circle inversion preserves angles, since the other types of transformations are dilation and isometries, translation, reflection, rotation, which trivially preserve angles. Furthermore, Mobius transformations map generalized circles to generalized circles, since circle inversion has this property. A generalized circle is either a circle or a line, the latter being considered as a circle through the point at infinity. Note that a Mobius transformation does not necessarily map circles to circles and lines to lines. It can be mix the two. Even if it maps a circle to another circle, it does not necessarily map the first circle's center to the second circle's center. Projective matrix representations. With every invertible complex 2 by 2 matrix A, B, C, D, we can associate the Mobius transformation f of z is equal to az plus b divided by cz plus d. The condition AD minus BC not equal to 0 is equivalent to the condition that the determinant of above matrix be non-zero, that is, the matrix be invertible. It is straightforward to check that then the product of two matrices will be associated with the composition of the two corresponding Mobius transformations. Now coming to fixed points. Every non-identity Mobius transformation has two fixed points, say gamma 1 and gamma 2, on the Riemann sphere. Note that the fixed points are counted here with multiplicity. The parabolic transformations are those where the fixed points coincide. Either or both of these fixed points may be the point at infinity. Determining the fixed points. The fixed points of the transformation f of z is equal to az plus b divided by cz plus d are obtained by solving the fixed point equation f of gamma is equal to gamma for c not equal to 0. This has two roots obtained by expanding this equation to c gamma square minus of a minus d gamma minus b is equal to 0 and applying the quadratic formula. The roots are gamma 1 2 is equal to a minus d plus or minus square root of a minus d whole square plus 4bc divided by 2c, that is equal to a minus d plus or minus root of a plus d whole square minus 4 times ad minus bc whole divided by 2c. Note that for parabolic transformations which satisfy a plus d whole square is equal to 4 times ad minus bc, the fixed points coincide. Note also that the discriminant is a minus d whole square plus 4cb is equal to a minus d whole square plus 4ad minus 4, which is equal to a plus d whole square minus 4, which is the trace square of the matrix minus 4. When c equal to 0, the quadratic equation degenerates into a linear equation. This corresponds to the situation that one of the fixed points is the point at infinity. When a not equal to d, the second fixed point is finite and is given by gamma is equal to minus of b divided by a minus d. In this case, the transformation will be a symbol transformation composed of translations, rotations and dilations. Z goes to alpha z plus beta. If c equal to 0 and a equal to d, then both fixed points are at infinity and the Mobius transformation corresponds to a pure translation. Z goes to z plus beta. Now I can summarize the points. Mapping is unavoidable since the explanation is very much easier when we consider the complex functions graphically. The requirement of a 4-dimensional space is not possible in this 3-dimensional world. Therefore, we take two complex planes, call one of them as Z plane and the other W plane. The basic mappings like translation, rotation, inversion, magnification, etc. are explained with examples. Now you can try for the coming questions. Question number 1. Find the image of the circle mod z equal to 2 under the transformation W is equal to z plus 3 plus 2i. Second problem. Determine the region in the W plane in which the rectangle bounded by the line x equal to 0, y equal to 0, x equal to 2 and y equal to 3 is mapped under the transformation W is equal to root 2 e raised to I pi by 4 z. Third question. Find the image of y minus x plus 1 under W is equal to 1 by z. Fourth question. Find the image of the semi-infinite strip x greater than 0, 0 less than y less than 2 under the transformation W is equal to Iz plus 1. Show the region graphically. Next question. Show that W is equal to 1 by z maps circles into circles. You can refer the textbooks and websites. Complex Variables and Applications, 6th edition by James Ward Brown and Ruel V. Churchill, published by McGraw-Hill International Editions. The next one, Complex Variables, Introduction and Applications by Mark J. Ablowitz and Athanasius S. Focus, Cambridge Texts in Applied Mathematics. Another one, Complex Variables by Herb Silverman, Houghton Mifflin Company, Boston. Hope that you have enjoyed this session. We can meet again with another topic. Thank you.